This is such a perfect piggyback. Thank you, Aubrey. We're gonna Aubrey was really looking at this kind of macro scale, and we're gonna dive a little bit into the micro, looking at specific sites, and then looking at this kind of tool that we developed at Reclamation to try to help some of these projects and help some of these ideas move forward. Conceptually, let's see, there we go. So we're going to talk a little bit, we're going to focus mainly on wetlands today. Wetlands obviously have a huge overlap between all the endangered species that inhabit the valley here. So we'll talk about what they are, what's wetland hydrology, and then how do we characterize wetland hydrology using gauge data. We'll talk a little bit about a proposed project in Las Lunas, and then how we used 2D hydraulic modeling to try to estimate where wetlands will occur. So what is a wetland? The federal definition from the Arid West Regional Supplement is that one key feature of the wetland is under normal circumstances they support a prevalence of vegetation typically adapted for life in saturated soil conditions. Many waters in the United States are unvegetated and thus are excluded from the Corps' definition of wetlands, although they may still be subject to the Clean Water Act. So the Clean Water Act regulates wetlands. It regulates the WOTUS, right, which is the waters of the United States. Wetlands are included as part of the WOTUS, so is open water, right, obviously. So there's three components that make up a wetland in the federal definition. Those are hydrophytic vegetation, and that's a community of macrophytes. I'm just going to read this so we're all on the exact same page, because these are legal, this is actually legal definitions that we're all required to go by. So the hydrophytic vegetation is basically macrophytes that occur in areas where inundation or soil saturation is either permanent or sufficiently frequent and of sufficient frequency and duration to exert a controlling influence on the plant species. The second characteristic is you have to have what's called hydric soils. Hydric soils are formed under conditions of saturation, flooding, or ponding long enough, during the growing season to develop anaerobic conditions in the upper part. So again, we're talking about duration of flooding, duration of inundation. And then finally, there needs to be wetland hydrology. Wetland hydrology indicators provide evidence the site has continuing wetland hydrologic regime and that hydric soils and vegetation are not relics of a past hydrologic regime. So, so when we talk about federally regulated wetlands, this is how they are defined. They have to have these three components: vegetation, soil, and wetland hydrology. So what is wetland hydrology? The Corps conveniently gave us this very nice, clean definition for wetland hydrology. Wetland hydrology is, this standard requires 14 or more consecutive days of flooding or ponding, or a water table 12 inches or less below the soil surface during the growing season at a minimum frequency of 5 years in 10 or 50% or higher probability. So this is a very nice, clean definition for what is wetland hydrology. The National Engineering Handbook, produced by the NRCS, took this definition and developed a very simple algorithm where you can take a gauge, a stream gauge, and translate that stream gauge data into quote-unquote wetland hydrology, meaning the value where ponding or inundation is likely to occur 14 or more consecutive days for 5 out of 10 years, right? And so basically the idea is you take each record, you take each year, then you cut, so you're cutting down the year, then you cut that down to the growing season, and then you take a moving 14-day window through that data, through the growing season data, and pick out the minimum 14-day value from each of those, that moving window. And then, so now you have these 14 days, then you take the minimum value for each year, right? So from these minimum 14-day values, you take the annual maximum. So what is the maximum value of the 14-day minimum? Okay, it's a little confusing, but fairly straightforward once you kind of get it in a spreadsheet. And then of those 14-day minimum values of the annual maximum, then you do a probability to see where the 50th percentile is. So pretty straightforward, basic kind of spreadsheet type of analysis. We did this at the Bosque Farms gauge. And what we found was that the water surface elevation associated with a discharge of 817 CFS represents the inundation level likely to occur at least half the time during the growing season and persist for 14 consecutive days, right? So that's the value that you need. That's the value that represents, hey, as long as we get to there, we're going to get 14 days of it. It's going to happen every year, and we're likely to see vegetation and soils in those locations. So that's all well and good. So what does that mean in terms of the ground? So now I'll talk just briefly about a proposed project that we're working on. This is just upstream of the Route 6 bridge in Las Lunas. Maybe you all are familiar with that. It's a project to improve both the conveyance capacity and the habitat, and I'll show you what that looks like in a second. We used LiDAR and field cross sections to create a geometry, existing terrain geometry, and then we built a 2D model with that existing terrain to see when overbanking was occurring, when water was getting onto the levees, etc. And then we did about 10 different test terrains. Let's see. Is that the the bottom one? Oop. The pointer, yeah. A star. Oh, I was pointing into my hand. Okay. So like, for example, you can see here we cut a big side channel. We actually widened an existing side channel. Here you can see we cut a little side channel and connected it back to the main channel. So kind of building on what Aubrey was talking about, this is our process. We try a lot of different iterations. We know that entryways and exitways always are sedimenting in, and so what is the likelihood? Should we be building these side channels? What's the impact of a side channel versus the impact of building these terraces? And you can see here, this is the terracing that we proposed, and this is the final design, what you see over here. And what we decided was basically to focus on these bankline terraces and not focus on the side channels so much, mainly because we know those side channels are very likely to inundate, and thus reducing the impact of any work that we do over a longer time horizon. Let's see, what do we got next? So it wouldn't be, I would lose my geomorphology membership card if we didn't look at some aerial imagery, some historic photos. I was really hoping this was like a huge screen so you guys could all see it better, but feel free to move up if you can't see. This is 1935, so this is pre-channelization, but not pre-levee. You can see the levees there, and you can see that the river is right up on these levees in a lot of cases. Here's Route 6 bridge. And then in 49, you can see there were some large floods in 41, but the late 40s didn't have a lot of flooding. And then again, you can see that now, between these years, we had quite a bit of vegetation colonization coming in to some of these areas that were once just open, active channel. And then in 62, you can see here that they've actually put jetty jacks into the middle of the channel there. It's hard to see. That's, like I said, I was hoping this was bigger, but you can also see jetty jacks that they've put in here. And then they've actually done some dredging through here to try to straighten the shot toward the bridge. to try to protect the bridge abutments. And so, so you can see a pretty dramatic change. Some of the vegetation hasn't yet, and the material hasn't yet deposited behind these jetty jacks, but hopefully you can see those and their tiebacks here. So this is literally just after they were placed in this area. These jetty jacks are placed all up and down the valley. So now let's fast forward 40 years to 2002, and now you can see, boy, those jetty jacks sure did a good job, right? So all the material behind the jetty, all the land behind the jetty jacks has all aggraded, right? And so all that material has gone through the jetty jacks, deposited, and then has aggraded. So now we have elevated floodplains with a very defined channel by 2012. But the other thing that's noteworthy is there's not a whole lot of vegetation within those jetty jacks in what we call the active channel, right? Active being because the sand is moving, vegetation can't grow. By 2012, you can see, well, we have quite a bit of vegetation now growing in between those jetty jacks in that 600-foot channel. And then this is data that we just recently collected from 2022, and you can see the narrowing of the channel and the vegetation encroachments that's occurred over these past, really, just 2 decades, but really even just between 2012 and 22, there's been quite a bit of vegetation colonization through this reach. The cause of the narrowing, kind of going back to Aubrey's presentation, is the idea that there's an absence of large flow events. Those large flow events kind of blew the channel out, removed a lot of the vegetation, maintained that width. And then the prolonged low flows, right? We're irrigating the bosque every year, right? So that vegetation never gets a chance to kind of die back because we're watering it. So the consequences of the narrowing is a loss of channel capacity. This kind of, in a habitat sense, is a little complicated because what it means is that it's overbanking at low flows. You could make an argument that that's a good thing, and in some cases, but from an infrastructure protection perspective, there's a line where going overbank at too low a discharge now becomes an issue, right? So this narrowing, now we're getting overbanking through this reach at a third of the discharge that we could see maybe just 10 years ago in 2012. The other problem with the narrowing is homogeneity. So we end up with kind of a canal-looking stream over a whole range of discharges. So anything from way down to 200 CFS all the way up to 2,000 CFS, the river is basically a canal through there. Once you get over that 3,000 and you get overbanked, now all of a sudden you've got like, it looks like a marsh out there because there's water everywhere. But in between those ranges, you've got basically a canal. So there's little shallow water habitat, which is what I was just trying to convey. It's often associated with deepening, but here, interestingly, in this Las Lunas area, the bed is actually quite stable. And that's why we're seeing the channel capacity loss, because we have narrowing, but not deepening. Upstream in Sandia, you have narrowing, but you have deepening. So the channel has a ton of capacity, and you can't get the water overbank. Here, because the bed is so stable, we're having overbanking at very low discharges, because we got the narrowing, no degradation or very little. So we sent some contractors out there to look for wetlands, which is part of our process, and lo and behold, they found wetlands everywhere we wanted to work. So you can imagine this was a bit of a hiccup in the plan, or a bit of a tope, like something we had to get through. I just posted some photos of these are, I think, what could safely be called bank line wetlands, since we're looking in the bank line. These exist in the bank line. For lack of a better term, we're going to call these bank line wetlands. You can see here some photos. You can see that some of the willows are probably 9 feet high, right? With DBHs of 2 inches or whatever. So some of these are very old relic wetland or willow. scrub areas. Some are a little younger, etc. There's some variety, but nevertheless, they found a lot of this kind of wetland out there when they looked. So what is that distribution of the vertical wetland? So this is kind of just a conceptual model of where those bankline wetlands would occur. On the lower end, there's the active channel that's preventing any bankline or any vegetation from occurring. At the upper boundary, we're going to use that definition that the Corps gave us, which is this 14-day 50th percentile discharge plus the 12 inches. Right, you got to add the 12 inches to represent the shallow groundwater that the plants are able to capture. So the wetland area is just basically all the terrain area. So it's not the surface, it's not the water surface, it's actually the terrain below the water surface, right? So what's the terrain area below this minimum 14-day plus 12 inches, and then you subtract the terrain area below that active channel water surface, right? So that would give you this space, but distributed throughout the whole model domain, wherever you were looking, right? So we can take this idea and then use 2D modeling to represent this location on the landscape. Where do these conditions exist on the landscape? Wrong way again. Okay. So again, I was hoping this would be bigger, but so these are some of the results of that effort. So in the blue, I'll try to walk you through this a little bit. In the blue here, we're looking at these blue. This is the open channel, they're the active channel, and what you could see if this was a little bit bigger is that that in the existing terrain, we were able to recreate the active open channel using about 500 CFS water surface elevation. So which is pretty much consistent with those of you who know the river, around 500, the river rarely gets below 500 CFS, and so that's about where we'd expect the active channel to occur. And then this is the active channel with the proposed terrain. And what you'll see is that some of these areas that we're proposing to lower are going to become open channel. Some of the areas that we're proposing to lower are not going to become open channel. And that all depends on the level of the terrace that we've defined, right? And then the other thing that's noteworthy is that, and I'm sorry about the scale, you can't see it here, but the area that we're proposing to lower here, actually half of it is going to be open channel and half will be, half of it will be active channel, half of it we think will evolve into wetlands, right? Because it falls within that window that I defined. So, so that again is all based on the height of the terrace that's being proposed. This is a comparison of the surveyed wetlands with the wetlands that were found in the model. And you can see that it does quite a good job of picking up the wetlands that they found down here. And this one, it picked up the wetlands here. Some of these wetlands, the model did not predict wetlands would occur there. And what that tells us is that those wetlands are actually higher than the wetland hydrology would predict, right? So what it's saying is that those areas, even though we're calling them wetlands, are actually much higher than what the model would predict and why we would think wetlands would occur there. They're there, but they're higher than that 800 water surface plus the 12 inches. And then here, lastly, we're able to predict that basically what this model shows is that all the lower terraces that we are proposing, we think are going to translate into wetland, right? So part of it is going to translate into open channel, part of it will translate into wetland. Let's see, did I want to say anything else about this? So basically in the terrain here, We have the proposed terrain will increase the open channel, active channel area by about 21 acres, and it'll increase the wetland area by about 1 acre, based on the existing and designed terrains. In conclusion, basically, this type of analysis using the hydrology and the modeling and the hydraulic modeling, it doesn't replace vegetation and soil surveys. I'm not saying you don't have to do those anymore. However, it is a quantitative strategy that can reasonably reproduce the wetland spatial extent, which we all love quantitative things. And this is a nice, clean way to do it. The prediction of wetland extent is consistent with professional judgment. Obviously, everything we do in modeling and data analysis requires professional judgment. There's large uncertainties around the shallow groundwater vertical and horizontal distributions. All we did was add that 12 inches. It'd be really nice to have a better idea of how that actually gets translated from the river out, across the floodplain. And then lastly, channel perching may over-predict the extent of wetlands. So with that, I'd like to thank my co-authors, Robert and Faith, and you all for your attention. Thank you.
Cool, thank you, Ari. Questions for Ari? Yes. Oh, I'll come back to you.
Thanks, Ari. Super interesting stuff. What I'm wondering about in terms of like what Aubrey was talking about, these conceptual models moving forward, and I know part of that Masong model that Aubrey referenced was the channel would narrow, then it would in size and sort of convey large flows. Do you think that's going to happen? A lot of sediment moved during this last runoff, a crazy amount, and what's going on in Albuquerque. I'm super curious about all this stuff, and like where do experts like you think this is going, and how can we get that sort of information? Yeah.
A little easy question there, thanks. Yeah, no, it's super challenging. It's super challenging. We have a tremendous amount of data and a tremendous both spatial and temporal scale that we're trying to wrap our arms around. I'm learning new stuff all the time. This area that we were just looking at actually was one of the early levees that were built. So there was only a few levees that were actually built through the valley back in the 30s and 40s, and this was one of them. So that's got to have a huge impact. The proximity to tributaries, to ephemeral tributaries, has a huge impact. Those tributaries add coarser material and create kind of a bed stability around those tributaries. Has a big impact. The other big impact is obviously coachity. We just finished, I'm trying to just throw stuff at you because your question's so big, but one of the pieces that we're learning, that we learned recently, is we just did an analysis on the suspended sediment at Central Avenue versus at the Jemez. And what we found is that in a lot of these big years, the Jemez can be about 30% of the suspended sediment that we see at the Central Ave Bridge. So all those kind of management activities, we made that big change at Jemez where we started to release the sediment again. Turns out that's having a huge impact on the river. So there's a lot, and I wish I had a better answer, but we're every day we're learning new stuff and trying to improve what we do. So the idea is this is just another tool in our toolbox to trying to get at, the changes that we're seeing out there.
Thanks, Ari. Mm-hmm. Really interesting presentation. Mm-hmm. Kind of one comment and I guess one or two quick questions. When you're describing some of the impacts of sort of the extreme loss of channel capacity, I mean, obviously, the threats to the flood control system is one, but just the loss of water to the system, which, is good for the Bosque, but not very good for our Rio Grande compact debit. So that's one point. And then, are you thinking that the wetlands that would be created through this terracing are you thinking of them as being sort of replacement for any wetlands that are potentially lost? And then I was wondering too about your gauge analysis, for the wetlands at Bosque Farms. Is that applicable just really to the project area, or what's the spatial area that's applicable to?
Yeah, okay. So I'll go backwards. I think that the Bosque Farms, the gauges vary quite a bit from location to location, if anybody's spent any time looking at these gauges. So I definitely think that anything that you get from that gauge is gonna be only apply to that location. I wouldn't apply that value downstream or upstream for that matter. It's definitely unique to that location. And then in terms of the wetlands and being a replacement for the wetlands that we're taking out, that is very much the idea. One of the things that we talk about water management and sediment management, and one of the things that we think we're observing is the lack of those large floods is producing a more homogeneous river. And so this project and building these terraces, the concept is basically to mimic a large flood. What would a large flood do? It would rip out the vegetation, it would create some heterogeneity in the channel. And then we know these surfaces are going to deposit. We know that vegetation is going to grow there. It's just a matter of how long does it take, what's the hydrology between the project and the subsequent years, right? If there's a lot of water, it might take a while for the veg to regrow. If there's a bunch of dry years, then chances are it's going to grow very quickly. But we know it's going to grow back. So the idea, yeah, is to basically take those wetlands where we saw that the willows were 9 feet high and translate that to a dense willow stand that is more waist high than 9 feet high is eventually over time, right, is what we think is going to happen. Yeah.
I think we can take one more question.
Okay, thank you. Hi, Ari.
Hey.
Thank you for the presentation. Gina Delarusso.
Yeah.
I was wondering, so looking at it from an ecosystem perspective, there are a number of different types of wetlands. And so is there an opportunity in your analysis to look at the quality and quantity of those different types of wetlands that could be established? Of course, slope of the surface you create is going to make a big difference there, and area. And so I was just wondering if that could be incorporated into your analysis over time. Thank you.
Yeah, I mean, ideally, that is definitely the goal. One of the things in researching all this, one of the things I was trying to figure out is how do we classify wetlands in the Middle Rio Grande? And it turns out that there's not a whole lot of effort in that. The one thing I could find was a 1996 report by the UNM biology department where they actually tried to build a taxonomic classification system for the vegetation. I don't know if you're familiar with that effort, but that's the closest thing I could find to actually a taxonomy of wetlands in the Middle Valley. And I'm hoping that gets more mainstreamed as we dig into this stuff. But yeah, ideally we'd be looking at, we don't just call them wetlands, that wetlands have different values and structures, et cetera. Yeah.
Great. I'd suggest looking at some of the data from Bosque del Apache and other refuges like Bitter Lake that have those lists of species that you would expect to find in more of the flatter feature wetlands.
Okay, great. Yeah, I'll touch base with you, Gina.
All right. Thank you, Ari.
Right on. Thank you.